I think we can start.
Okay, give me 1 minute.
Sir, your voice is echoing.
What happened?
Nothing, sir. Your voice was echoing before it.
I think now it's okay. Okay. So now there are how many students in the class right now? Seems to be 57. So I'm giving little talk on this cold atom for quantum technologies. And nowadays, quantum technology is a big field all around the globe, not only abroad. Now, Indian government also has started initiative to use the quantum technology, and there are many ways of doing this thing. So I will be giving talk how we are going to give the uh, using the cold atoms for this. And during this talk, I will try my best not to use any mathematics that you cannot digest. So I will try to keep as much as simple and so that whenever you have a question, you can always ask me. Okay.
सर आज आप क्वांटम एंटेंगलमेंट के बारे में बताएंगे.
Quantum entanglement तो next maybe next class I can tell, because I am not going to tell in this thing, because before that you have to understand superposition, then before that many things are there. So I will just give the idea. Main purpose of this talk to give the idea how people are using it, because atoms are not trapped, then how can you do the entanglement? First you have to trap the
Okay.
atom. Okay. So here I'm just showing one picture I have taken from magazine, showing some. This is
Excuse me, sir.
some. Yes.
Sir, can you please record the class for future reference?
There is no future. I'm just giving a talk, and next this weekend I will also take the exam. Okay. Very simple talk. There is no need to problem. I will share the slides. That's all. Okay. So I am showing here in this picture, this red color is some beams, laser beams are going on. There are this green color, you can see the coil, some magnetic field we are generating. In the center, we have a zero magnetic field. So I will discuss all this thing in coming slide also. So here I am writing particle interferometry with the ever bigger and more complex object. So you must have seen this one simple equation, de Broglie wavelength, lambda is equal to h over mb, and I am sure all of you know, because this is in the your class 12 book. So here h, what is h?
Planck's constant.
Very good. M is the mass of the particle and b is the velocity. So first I will discuss with the m, then we'll see what will happen with the v. So very famous equation. So here I'm just showing some particle, for example, photon, it has a zero mass. Electron, I'm writing all this mass in terms of proton mass. Electron mass, it was discovered 1950, neutron, atoms, and so on. So if we are going to substitute, and this I'm showing the big buckyballs, I'm showing very heavy molecules. They have very more bigger mass. So if you substitute the value of these mass in this wavelength, to find out the wavelength, we are putting the mass here. So you see, when it's a less mass, we understand that lambda will be higher. As m will increase, lambda is going to be smaller and smaller. The same thing I am trying to show here. It's not in scale, just to graphical, my these cartoon pictures are there. Okay. As mass is increasing, wavelength is reducing. And then we have to make the atom cold. That is, I'm saying here quantum frontiers. So when we have to, how to make the atom cold, and what is the meaning of this atom is cold or not? So simple thing, as atom become cold, it means its velocity become less. So I'm again going to show you this de Broglie wavelength equation. So basically, our main purpose is this: we have to reduce this v. When we reduce the v, you can again make out from here that lambda is going to be increased. So let us say any particular gas, some helium, nitrogen, whatever we want to take, we take and we start reducing the velocity. As we start reducing the velocity, we will find lambda increasing. The same thing I am trying to show here. So in a room, or let us say in some experiment, we are taking one gas. So generally, mostly in the lab experiment, we take sodium, cesium, rubidium. Some gas form has been taken. The main thing is that making cold means we are reducing their velocity. We have to reduce the velocity very low. Zero we cannot reach, but we can reach very low. So temperature basically is a random jingle I'm saying here. And then thermal velocity, I'm going to compare temperature when reducing, thermal velocity will reduce. What happened to de Broglie wavelength? So I'm showing here when atoms are hot, thermal velocities are very fast, I'm saying. So de Broglie wavelength, you can see it very small. The moment we make it cold, thermal velocity will slow down. So de Broglie wavelength will increase if you compare with this formula. Because as the B reduce, the lambda will start increasing. The same thing I have shown here. I think all of you will agree with this.
Yes,
All of
sir.
you agree? As we
Yes,
reduce
sir.
the velocity, so it is going to reduce. Okay. So we are going to get the big de Broglie wavelength. So how cold is cold? Question is this. I'm saying. So temperature, I'm just showing, suppose when you have to measure the temperature to make sure this is cold or not. I'm just showing you one thermometer. And in this thermometer, I'm showing the Rudgi's temperature. This side I'm taking Kelvin, this side degree. This is just normal temperature, not right now temperature. Some temperature, 33 temperature in Rudgi. Okay. And then, you see, I said absolute Kelvin we are taking, I'm showing here. And Celsius temperature I'm showing this side. And just I'm dividing temperature here. Let us say 200, 100, and 0 degree I'm showing here. Okay. So again I've divided here. 100. I have come here to 250. You can say 150, 50, and 0. So if we start reducing temperature, if you go to Srinagar right now, recently -6 degree, -8 degree in Gulmarg temperature was there, somewhere here. If you go Atlantica, more lower temperature this side. If you go more down, air liquefies, more low temperature here. And this is outer space, you go some Trenton, some, I think, planet is there, temperature this much. And here, outer space temperature, it reach totally 3K. There we be reaching almost very low temperature, 3 Kelvin I am saying, but we are not reaching 0 degree. Okay. So absolute 0, it means all motions stops. Okay. Now I'm showing here the rubidium atom. So rubidium atom, you will listen from me many times because I am working on this atom. Main purpose of this atom, we are going to make quantum gates in the future, whatever this thing. So right now I'm just giving you a simple talk. So here I'm just comparing, suppose you have how much temperature, what will be thermal velocity, and how will be corresponding wavelength. So if I'm in the room temperature, let us say 300 Kelvin, so this rubidium has a velocity 300 meter per second. If you calculate the de Broglie wavelength, so we will get this thing near about this. And if I reduce the more temperature up to here, 300 millikelvin, then corresponding velocity will be this. The corresponding wavelength will be this. This is micron I'm talking here. If I go more temperature lower, so we are reaching 1 centimeter per second thermal velocity. And corresponding wavelength will be around, de Broglie wavelength will be 1 micron. And people have reached up to picokelvin also. But problem with this picokelvin, due to this Heisenberg uncertainty principle, then we cannot make out where the atom is. You cool down so much, so you must have read, if you have, someone of you have read the little more physics, delta P, delta X, which corresponds to H. If you making by you, some of you are disturbing the class. If I think if you are and you understand you are very intelligent, so you can leave the class. I have no problem. So if we reduce the velocity too much, it means momentum will reduce very much, but there will be uncertainty in the position of the finding where the atom is there. So we cannot make sure where is atom in the space. Atom is here or atom is there. We cannot make out. So people have reached up to the picokelvin. This MIT group, they showed, but they could not make sure where the exactly right now atom is there. That you must have read. You can take any book, either Feynman book or somewhere you can read uncertainty in this Heisenberg uncertainty. So you can make out from there. Though if delta P, you fix it, so there will delta X. If suppose this is reaching 0, so there will be a lot of uncertainty in delta X. It means you cannot make out where the atom is exactly. So let us go further. So we have to reach 1 nanokelvin, means up to this temperature that I'm talking here. And many groups are doing nowadays of this thing, but most of the groups are working within 100 to 200 nanokelvin, and that is more than enough to do many experiments. So what type of experiments they are doing, this thing that I will discuss in the coming slides. So this Bose-Einstein condensation, in the short form we say it BEC. Okay. Have you heard anyone this name?
Yes, sir.
Yes,
State
sir.
of a
Yes,
matter
sir.
with plasma.
Yes.
Plasma.
So
Yes, sir.
plasma is very
Before
hot. Plasma we cannot do. We have to very low temperature. So Bose is a Indian guy. Einstein, you already German guy. You already know. Extraordinary. And Indian contribution is also from there. Satyendranath Bose. So I just give the little history, what he did, what Einstein did, that I am telling here. So this happened in 1924, almost 100 years back. So Einstein, basically he did some work and he sent to the Einstein. He was a very shy major guy. So Einstein translated a paper of S.N. Bose which contained a new derivation of Planck radiation law based on statistical treatment of photons. Okay. And then later on, he used this idea, Einstein, and he worked and around this, after this paper, he worked in 1924 to 1925. Einstein presented a similar treatment for an ideal gas of indistinguishable particle at some conference name is there, a German conference. So you can make out some German word. So he presented this paper there in this conference. And what was that? That thing that I will show you in the coming slide. So later on, that was the history. And work from 1925 to 1980, nothing happened. Just remember, if any theory come in the, we do some theory, we do some experiment. If theory is there should be experiment. If there is experiment, there should be a theory. For example, when interference experiment happened, so Young did it. So he found when light, very famous statement, given light meets light, there is a dark. But he made theory also. You people have read interference experiment. Why dark is there? Why bright fringes are there? So he did experiment. He did the theory. Here theory was given, but in between people tried. From 1925 to 1980, people kept on trying. There should be, we should get the Bose-Einstein condensation. But limitation were added from this time 1925 to 1980. We had not very nice instrument to make the vacuum. We did not have a very nice laser system, because whatever I'm going to discuss in the coming slide, old atoms were made using the laser light. Even we say laser beam is hot, it cuts the material, but it will also make the atoms cool. How? That I will discuss in the coming slides. So laser cooling, in between, I'm showing some famous people who got the Nobel Prize. So I'm showing here Theodor Hensch, Shallow. They worked on some neutral atom initially. They gave idea. They got Nobel Prize in 1981, and Hensch got it in 2005, and so on. Some work were done on the ions. So Delmelt and this Wineland, they in 2012, 1989, and 1997. Then laser cooling. They got people, Steven Chu, Kohn Tanuji, and I'm just forgetting his name. And this is Eric Connell, Cutterley, Wyman, all this 2001. Atomic BEC made. So 1924 work started. Cooling happened in 1997. Cooling happened little before, but Nobel Prize was given here. I think by 1985, cooling was done. It took many years. But Nobel Prize was given because when their application started coming, on that basis they got the this Nobel Prize. Okay, so I'm coming to the more details to understand the BEC, Bose-Einstein condensation. So this is the coldest matter in the universe, because we have to make the atom very cool. What is temperature? Question comes, what is temperature? This is a measure of energy. The more temperature, it means it has more energy. If a low temperature, it's a less energy. Simple logic, you can also say. So motion, suppose anything going, basically that is also energy. Anything moving, that you already know. The question is, what is temperature? A measure of energy. Zero temperature means zero energy. Just think in terms of the atom. Atom is moving in a free space. It's moving, it depends upon the outer temperature. And if it stops, it means it has no energy, it means it has no temperature. So how cold it is in our laboratories? So I said nano Kelvin people have already reached, more than 1 million times colder than interstellar space. So much cold temperature has been developed in the laboratory. Many laboratories all around the world, not only in the world, even in India, many laboratories. So what happened to atom at low temperature? So we will understand this. They slow down from 300 millimeter per second. They reach to the 1 centimeter per second. That much temperature reduce. Even we can go more lower than this. So once this happen, all the atoms they behave in the same way. So that's why I have written here. They march in a lockstep. All the atoms they behave in the same way. Okay. So I'm just showing this paper published in Science. It was 1995. VC was made by Eric Cornell and group. They are showing this particular. You can see here some atoms. They are showing they are marching in a lock. So what is a marching in log that I will show you in the coming slide. It will like more and more I will compare, then things will be clear to you people. Okay. So cooling a gas of atoms. So I'm just showing here in this picture, atoms are going some this direction, that direction, this thing. And temperature is, so here you can see 1 millikelvin of the range. This is a 10, 100, so that range within some temperature is here. The atoms are going randomly in all direction and they have velocity almost just like an aeroplane. What is aeroplane velocity, by the way? Anyone can guess in kilometer per hour? Bolo bhai.
800 to 1000.
6 to 700. 6 to 700.
So it is less than sound speed, that is for sure.
That of course. So that is fighter planes. They go to by 2 Mach, 3 Mach, 3, 4 Mach. We say na ki if they are twice a sound speed, 2 Mach, 4 times of sound speed, we say it 4 Mach. You must have read MACH. These are our fighter planes.
Yes.
Okay. So then we reduce the temperature. So I am showing here some of the atom velocity start reducing when temperature is thing, and more reduce. Then as the temperature reducing to de Broglie wavelength, the corresponding wavelength start coming. That I am showing here in this figure. So what happened? That you already know, given by I showed the Louis de Broglie. He also got the Nobel Prize in 1929. And I don't know whether you heard or not. He published his PhD thesis. I heard it is only 4 or 5 pages thesis. That's all. 4 or 5 pages. And then we reduce more temperature. I'm coming here. So you can see almost 10 microkelvin somewhere. Then atoms are moving just like a snail. I'm showing here. It was a plane. Now we reach to the snail. But as we reducing the temperature, you can see de Broglie wavelength size increasing. And we reduce more, then it become more bigger. And what happened during that time, many atoms, they behave such a that their wavelength, the de Broglie wavelength, they start overlapping. So they start going to the bottom of their system. What is the bottom of the system? That I will discuss in the coming slide. Because initially I'm trying to make my lecture as much as simple and smooth, you people should understand. So this is I'm showing here whatever discussed by the whatever discussed by the Bose and Einstein, atoms are described by the same quantum wave. So all the atoms to go to the lowest of the system. So let us say one system is there. Suppose if I am saying this is a bucket, they all reach here. But this is not a bucket. If any one of you have read harmonic oscillator, we try to make a harmonic oscillator and they reach all the atoms in the ground state of the harmonic oscillator. And then they behave as a giant wave because all of them have the same phase, same log, as I showed log, and they behave in the same way. So just remember right now. And we are very low temperature at that time. So all these things, whatever I was telling here till now, I have summarized everything. When temperature was very high, thermal velocity, density proportional to the 1 over d cube. This I'm showing d here. As we start reducing the temperature, why my slides are jumping. As we start reducing the temperature, then de Broglie wavelength start increasing. And I showed de Broglie wavelength is equal to h over mb, or we can say 1 over t, basically. At some critical temperature, this de Broglie wavelength and d, separation between the two atoms, they become equal. The matter wave start overlapping. We get at some critical temperature, the Vc, and when temperature is T equal to 0, at that time we get the pure BEC. At that time we are saying giant matter waves. So this matter wave is overlapping and giant matter waves. But BC start at some critical temperature. That's what I'm saying is no need to go to at T equal to 0 just before it start coming. Obviously, as I'm saying, when T is equal to 0, but T is equal to 0 is an ideal condition that never happen in the, we will never reach. I said people reach nano Kelvin, they reach pico Kelvin. But T is 0, T is equal to 0 is ideal condition. I think all of you will agree because T is equal to 0 is not so easy thing. Because there is a noise always in the nature. So any question up to here?
So this critical temperature is absolute or relative, like whether it depends on different nature of different atoms or not?
See, when people started working initially, I'm talking again around 1985, people were working rubidium, sodium, cesium, many things were there because they are all alkali atom. They have a single electron in outer shell. Plus also depend because when we are doing this experiment, we need a corresponding lasers. With the same laser, you cannot work with the rubidium. Rubidium has a different wavelength. Sodium has a different. Cesium has different. Lithium. At that time, people started. Nowadays, people are working many more atoms. Even they had reached to the ytterbium, strontium, and I will tell you all this thing in coming slide because why people are jumping here. And for example, I am working on rubidium. Whatever I am working, because I will be using rubidium atom to make the quantum gates. Whatever quantum computing gates, I am working on it. It depends upon how much facilities you have, because these experiments are very expensive. You will be working around 10 to the power minus 12 torr vacuum. 1 torr means 1 mm corresponding to 1 mm Hg pressure. You need a very good vacuum, then corresponding laser. Laser should be very ultra stable. Their frequency should be fixed. They should not go left and right, and lot of electronics. Because in present in this century, everything become very sophisticated. We are just working engineering, all these engineering cutting edge experiments are going on all around the world. So you have to be perfect in everything. That Raman age has gone. Raman did very simple experiment and gave very nice theory and everything. Got the Nobel Prize, one and only one in India so far. But nowadays, everything has become very sophisticated. And I'm sure most of you will take these things in the future. Okay.
Sir.
Yes.
Sir, means that means that Bose-Einstein condensate that theorized that there would be a giant matter wave at t is equal to 0.
Yeah.
So, but there is no any kind of experimental evidence, right?
No, I said a nano Kelvin, pico Kelvin we have reached now.
But
BC already made.
Equal to
People
0.
got the Nobel Prize.
Yes, sir.
PC is already made. I should go back. The people have already got the Nobel Prize for this also. I go back 1 minute.
But sir, that is for pico Kelvin and nano Kelvin.
No, nano Kelvin enough. They are able to show all the feature of the BC.
But like, yes. Sir, can they be like virtual particles which pop out from the space time and then again they disappear? Something like that can happen or what?
No. They did. They got it. Whatever the theoretical model says, what is the feature of the BC, they showed everything.
I'm talking about absolute zero. I'm not talking about.
Absolute zero. That depend upon what you are doing these experiment against the nature, because nature doesn't provide you 10 to power minus 12 torr vacuum. These are very ultra. This experiment to be cannot reach t equal to t0 is equal to a ideal condition. We are fixed. But before going to, if you are going to micro Kelvin, nano Kelvin, pico Kelvin, you cannot reach. Our measurement tool is also very perfect, no? Because atom stops. It is difficult. If you go in even in a vacuum, you have hold the atom. You cannot say you have hold, because even your laser you are using, that has also some jittering. It is not as fixed. That is also jittering. That frequency also has some jittering. Even if you do the jittering, so still that atom will be oscillating. Very small oscillation will be there. So that will give the temperature. Just if we are saying if we are holding the atom, but our measurement tools also become a very sophisticated. They are able to measure the temperature. Have you got my point?
Sir, like, can't we consider them like they would become a virtual particle and then they would disappear? Like this also it can be happen.
No. How will they disappear? Where can they disappear? They are there.
It's like virtual particles, sir.
Virtual particle means virtual though, but atom is there. How can it disappear?
Means like that Hawking radiation, he proposed that there would be like a virtual particle would pop out and one would come out of the black hole, one would sink in the black hole.
So like that's why those theory finished. Suppose any experiment you are doing, there should be any theory, there should be a, that is the only whatever talking, that is a statement, but nobody has done experiment on it. Whatever I'm talking, this is real experiments.
It means we don't have.
Whenever any theory proposed, there should be a evidence proof. I'm talking about the proof is there. People have done the experiment, they have measured it.
Okay, sir. Okay.
That's why, see, a lot of theories comes, but whenever there is no experimental proof, they always disappear. Any theory, if supported by the experiment, then they move forward. Just remember. And whenever any experiment comes, there should be always a theoretical proof.
Okay, sir.
Sir,
yes.
How can we measure such nano Kelvin temperatures?
That is a good question, very good question. So I tell you. Anyway, I will show you in the coming slide, but right now I can tell. See what we do. Suppose we have atom here, okay, and we put the light, laser light, and we do the imaging on the CCD camera. Not a very simple CCD camera. Whatever I am using, we call it EM, electron multiplier CCD camera. Even single photon comes, it can detect. So we take the images. Suppose I take one image at let us say 0 second. Let me, I should not say at time t is equal to 0. And then I take another image at t equal to 20 second. How much separation between them? Suppose atom was here. And then we know the separation. And then we can find out what is the velocity. Well, not velocity, what is the distance? From this distance to this distance, it has been in 2 seconds. And then we can measure it, what is the velocity. And from velocity, we can find out the temperature, because we cannot measure by any probe. We are using, we cannot touch it from outside. Suppose anything is in a vacuum, atom is in the vacuum, we don't have any tool to touch it. We are just doing all things using only laser beams, putting from outside and then doing the imaging on the CCD camera. And then we have to find out the position here, time, separation, and all these things.
Sir, how do we know that the same atom has moved? It can.
This is not a one single atom right now. Let us say we have a 10 to the power 14 atom. Let 10 to the power 4 atoms. 4 to 5 atoms. They will be in a group. It will be in the laser. We are holding with the laser beam. Let us say this is a laser beam. I am holding atom here. And you switch off the laser beam. The moment you switch off the laser beam, this atom will start falling due to the gravitational force, and their area will start increasing. Whatever was here and whatever here, separation difference is there. From there we estimate how much has changed in the dimension. From there we get the what is the temperature.
Okay, sir.
Okay, because you can, if you touch anything from outside, then it will be not a quantum world. Quantum world, you don't have to touch from outside. And whatever this VC I'm talking, it's a quantum gas. We reach to the quantum world. It's no more classical world. Okay, so T equal to 0, I said this is the ideal case. But nano Kelvin is more than enough to do many experiments. Okay. So what is the goal? So I'm showing here goal, main goal, use ultra cold atoms and quantum gases. Quantum gases means BEC. To gain fundamental insight into quantum mechanics to build the quantum devices. So fundamental insights to understand the quantum material. So here I am showing you one magnet is levitating. And we can also make a atomic clock, quantum devices. So these atomic clocks, very sophisticated. And if you use them in 5,000 years, only 1 second will change. That much of sophistication is there. I will also come one by one these things. So many body system, superconductor I'm talking here. So here, if you see inside, they are inside this I'm showing you there a pair of electrons. Here I'm just showing a pair. So intricate quantum motion of electron gave rise amazing microscopic behavior that we want to understand. But thing is that and normal, if you take magnet, it's very complicated, complex structure. But to understand, we can take some pure gas, let us say rubidium, cesium, whatever, and we can make a pairing there. People are already made the pair between the two atoms, and they have done the study. Basically, you can say artificial matter has been made in the laboratory, pure artificial, and then you study them. Already going on around the world. If you want to know, I can let you know. Then simulation of classical computer. So memory requirements for n spin half particles I'm showing here. In classical computer, I'm just showing there are n bits describe state of the system. So here I'm showing some up, down, I'm showing here. But in the classical computer, in the quantum computer, things comes like this. Suppose here we have taken 1, 2, 3, 4, 5, 6, 7, 8. Here I'm so 1, 2, 3, 4, 5, 6, 7, 8. 8. I have taken the electron. Here one's on all up, then one down, and the one this down, and so on. We can make superposition of so many states that I am showing here. So basically, I am showing here 2 to the power n complex number alpha I describe the state of the system. So many, just by using the 8 spins, we can make 2 to the power 8 states to describe a system. So already work is going on all around the world. I'm just showing you most powerful computer in the world. Fukaju leak in Japan. So you can see some numbers are written. 30 MW, 500 petals, 480 petabytes RAM. You know what is petabytes? How much? GB? 1 petabyte is 10, maybe 1 million.
Sir, 10.
1 million gigabytes. 10 to the power 6. मेरे कंप्यूटर में my computer here only 32 GB. And see what they are using. And if we want to make such a powerful computer, we need only 56 spin of 56 atoms. If we use 56 atom or 56 superkinetic qubits, whatever Google and IBMs are using right now, that can make such a powerful computer. Just compare where we are reaching now. Okay, a few more. I would like to give you a few things more. The ultimate supercomputer I'm showing here ki store one complex number in each atom. Suppose store one complex number in each atom, then you need 10 to the power 80 atoms in the visible universe. In the visible universe, we say that there are so many atoms are there. And here why I'm giving it, just to compare. If we take 270 spins or 270 atoms, that can store that much information. The difficulty lies in entanglement of the system that people are working nowadays. Once we get very nice entanglement, so we can do so many things that nobody can imagine. The solution, use quantum. 1 minute. The solution is use quantum computer, but we neither have a good quantum computer right now nor a good quantum algorithm. So many groups are working right now around the world, me also. So have you understood what I have said up to now here?
Yes, sir.
Yes, sir.
Yes, sir.
सर इसमें चाइना आ गया है ना सर हमसे? सर चाइना कोई अचीवमेंट रीड किया था मैंने सर कुछ दिन पहले.
क्या चाइना हम लोगों से आज बहुत पहले से आगे यार. हम लोग टीम वर्क नहीं में फुसटी हैं इंडियंस लोग. We are not good team work when it comes to the team work management. We are not good.
सर मतलब मैंने रीड किया था कि उन्होंने क्वांटम एंटेंगलमेंट किया था, मतलब काफी हाइट से.
ऑलरेडी हो चुका, नहीं ऑलरेडी कर चुके हैं. चाइना से पहले यूरोप में भी हो चुका था. Already China was good only because they sent this entangled photon in the space that is up to 4,600 kilometers. So cryptic information can be sent from one place to other place. Indians also did, but later on we have also done. Our ISRO group has done already. And thing is that we are a little behind. Problem is this. So you can check, a lot of work is going on. Even if you search quantum technologies, you will write down Indian government, you will also find what is going on in India. But the only thing is that in India, this work started only 3 years back. Okay, then go further. So immediate solution, quantum simulation. We are also doing quantum simulation. Quantum simulation, this we are just now, I use one word, artificial matter. We are making artificial matter using these cold atoms. Use well-controlled quantum system to simulate difficulties to access the quantum system of interest. So basically, this state, first time this thing was given by the Feynman. Maybe in the next lecture I will show you. Even I will show you if I would take the 2-level atom and we just do the simple modeling of this, and I will show you this is nothing. It's just like a quantum gates that we use in the quantum computer. That I will show in the next lecture. Okay. So this I'm showing here some atomic. This is the clock we are making actually. So this is my last slide because almost lecture is finishing. So basically I'm showing the quantum model. Basically I'm showing it when we are doing the things, we have to write Hamiltonian. I don't know whether you people have heard the word Hamiltonian or not. Don't worry. Basically this is the energy, kinetic energy, potential energy you add something like a Hamiltonian. So to theoretically I'm talking, and then quantum simulator, whatever I'm showing here, we trap the atoms. This is I'm showing is of each atom, an atom trapped in a uniform way. I mean, we can make whatever we nowadays atom can be trapped in whatever way you want to trap. We can trap it. We have reached up to that sophistication in last 2-3 years. So you just put in order all the atoms. Here I am showing in the 2D, you can put in 3D also, and then you do all the other studies. In interaction between the two atoms, many atoms, we can do everything. So this is called simulation. So theoretical concepts are clear. So here I'm showing we trap the atom, whatever I'm showing here, trap the atom, then interaction between them. We can control the inner state, whichever state we want to put the atom inside, we can also put. That we can do right now, everything. So for all this purpose, we need a ultra cold atom. Okay, atom should be controlled by us only from outside. So as I said, just a few slides back, we will be using this thing to understand the quantum mechanics and quantum devices. So quantum devices, basically mainly quantum clock, atomic clock I should say. So by atomic clock, see pendulum, you already know, used many years, 15th century, 16th century, 17th century, and now we are on the atoms. So I just would like to show why we are doing this thing. Okay, to get the high accuracy, high tension frequency. So for that, it depends upon the optical tension, then narrow tension. It has a line width of the whatever line width means when we are plotting frequency versus in basically frequency, this frequency, tension frequency, let us say center frequency omega naught, that is of the order of megahertz, very narrow. Even we have gone less than hertz, you can make out from here, millihertz, which means we are less than 1000 of down from the 1 hertz. Last signal we use many atoms, then disturbed by the other atoms, to use gas atoms, because gas atoms a little far, so they don't neutral atoms, they don't interact with each other, so much better than compared to the ions. Initially people were making the atomic clock using the ions, now but we have found neutral atoms are much better. And observe for a long time, cool atom to stand still, but I said we cannot reach to the standstill, but we reach almost zero, but not zero. So that I said, one group in the US, they have trapped the strontium atom like this, and putting the laser beam there, and they are using this optical frequency comb. But basically, in the broad way, I would like to say, they have made the atomic clock, and as I said, it in 5,000 years, I said 1 second, not 1 second, even less than 1 second, change will be there. That much accurate atomic clock has been made. So now I just stop here. Do you know why you are working on the atomic clock? Can you tell? Anyone who has read?
To demonstrate
Sir,
the
to reduce the time dilation effects that we observe because of the motion.
You are a little right, right. But just for example, think like this. You heard about the GPS?
Yes, sir.
Global Positioning System. We have many satellites, around 16, 17 satellites. All of them have to be synchronized at the same time for better and better accuracy. Suppose you want to fire the bomb somewhere, even your laser guided missile goes, they are controlling with the GPS. Even you have mobile in your hand. Okay, so you can make out where you are standing. So this is not happening only due to one satellite. 4 or 5 satellites participated to find out the accurate position. Where are you standing right now? Okay. So I will come. Let us see how much I can finish. And right now, today, whatever I've told, we are reducing